5.3 questions. What determines the arrangement of electrons in atoms of different elements? How does the periodic table predict the arrangement of electrons in an atom? How can I indicate the arrangement of electrons in an atom? How can I tell which electrons in an atom are valence electrons? Terms: electron configuration, Aufbau principle, orbital notation. Pauli exclusion principle, noble gas notation, Hund's rule. Valence electron, Electron Dot Notation, ion, cation, anion. Why does it matter how the electrons are arranged? 5.3 Electron configurations. Electron configuration and the periodic table. The modern periodic table, which you will learn more about in Chapter 6, is actually organized by electron configuration, the arrangement of electrons in an atom of an element in its ground state. Atomic numbers increase from left to right across the rows. Each row number corresponds to the highest principal energy level for the elements in that row. Certain regions, or blocks, of the table indicate sublevels in which electrons are located. Let's look at how this works. As you read the periodic table from left to right, electrons are added to orbitals in the order seen on the table. We can use the preceding information to compare electrons in atoms of different elements. Take zinc and bromine, for instance. Both of them are in the fourth row of the periodic table, which tells us that both elements have electrons in principal energy levels 1 to 4. However, zinc is located in row 3D of the D block, while bromine is in row 4P of the P block portion of the same row. This tells us that the highest energy electrons of a zinc atom are located in its 3D energy sublevel, even though zinc has some electrons in energy level 4. Bromine, on the other hand, has its highest energy electrons in its 4p sublevel. As described more fully below, highest energy electrons are not necessarily in the principal energy level that has the highest value. There is overlap of sublevels from different main energy levels. Writing electron configurations. You should now understand how electrons are arranged in a neutral atom in its ground state. In neutral atoms, the numbers of electrons and protons are exactly equal. Since the periodic table is arranged by increasing atomic number, and since the atomic number is equal to the number of protons in an atom's nucleus, we can use the atomic number to determine the total number of electrons in a neutral atom. The Aufbau principle states that electrons must fill the lowest available energy sublevels before they can be placed in higher energy sublevels. In practice, this means that we can determine the arrangement of electrons in an atom by adding electrons to an atom with a lower atomic number, that is, one with fewer electrons. Progressing from hydrogen through the higher numbered elements, electrons add to the least energetic orbital possible. Generally, lower energy orbitals must be filled before higher energy orbitals. Hydrogen, Z equals 1, has one electron that resides in the 1s sublevel. Hydrogen's electron configuration, or arrangement of electrons, is written as 1s1. The coefficient 1 tells us that hydrogen's electron is in the first energy level. The letter S indicates that the electron is in the SS sublevel of the first energy level. The superscript 1 tells how many electrons occupy that sublevel. In this case, there is one electron in the 1s sublevel, which is also the only orbital in the atom. Physicists and chemists also use a special notation, called orbital notation, to illustrate the electron configuration of an atom. Orbital notation consists of horizontal lines representing the orbitals labeled by sublevel. Each electron occupying the orbital is written as an up or down arrow on the line. The opposite directions of the arrows represent the opposite spin that each electron must have to occupy the same orbital. The fact that two electrons in the same orbital must have opposite spins is one of the conclusions of the Pauli exclusion principle, first formulated by Wolfgang Pauli in 1925. The orbital notation for hydrogen is written as follows. Helium, Z equals 2, has 2 electrons when neutral. The second electron joins the first to fill the 1s sublevel. Helium's electron configuration is thus 1s squared. The 1s sublevel is now full, and helium's notation is shown below. Lithium, Z equals 3, has 3 electrons. 2 electrons occupy the lower energy sublevel, 1s. The third electron can reside only in the next higher energy sublevel, 2s. Its electron configuration is written as 1s22s1. Notice that lithium is on the second row of the periodic table. Similarly, the electron configuration of beryllium is 1s squared 2s squared. As shorthand for electron configurations, chemists often write the symbol of the element that fills the previous energy level in brackets before adding the next sublevels. Doing so shortens the notation and emphasizes the highest energy electrons. Because helium fills the first energy level, lithium's abbreviated configuration can be written He2S1. Because this last column of the periodic table is a group called the noble gases. This abbreviated form is sometimes called noble gas notation. When determining the electron configuration of carbon, Z equals 6, you have a choice in which blank to place the arrows. Its electron configuration is He2S squared 2p squared. But what about the orbital notation? Are the 2 electrons in the 2p sublevel in the same orbital, below left, or are they in different orbitals, below right? This question was answered by Friedrich Hund after he carefully studied the movements of electrons within the orbitals of a single sublevel. He determined that for orbitals of the same sublevel, the lowest energy state exists when the number of unpaired electrons with the same spin is maximized. In other words, Hund's rule states that as electrons fill a sublevel, all orbitals receive 1 electron with the same spin before electrons begin to pair up. Therefore, by Hund's rule, carbon's orbital notation is the second option. Notice also that there are 3 blanks for the p sublevel. These blanks stand for the 3 orbitals in the p sublevel, px, py, and pz. Review Table 5-2 to see the orbital notations and electron configurations of the next 8 elements after helium. Using the Aufbau principle and Hund's rule, you can determine the electron configuration and orbital notation of any element. Valence electrons. Atoms can have many electrons, but those in the outermost energy level are the most important because they are the ones most likely to be involved in chemical bonding. They are also the ones that give elements many of their physical and chemical properties. These special electrons are called valence electrons. Valence electrons are not necessarily the last electrons to fill an orbital. Rather, they are the electrons that have the highest principal quantum number, n. These are the electrons that occupy the highest numbered s and p sublevels, even in atoms that have higher energy electrons occupying inner d and f sublevels. Study the following example to see how this concept works. As you will see in the case with zinc in example 5-2, valence electrons can never be in the d or f orbitals because these orbitals are always filled after filling the s orbital of the higher energy level. Electron dot notation. Sometimes scientists represent the valence electrons of an atom using electron dot notation. Dots that represent valence electrons are placed around the element's symbol. Because valence electrons involve only the outer s and p electrons, a maximum of 8 electrons, no more than 8 dots are used. The electron dot notations for the elements in the third row of the periodic table are shown in Table 5-3. There is no standard way of arranging the dots. In this textbook, we will adopt the following convention. The first 2 dots, which represent the s valence electrons, are placed in a pair to the left of the element symbol, since the s block is on the left side of the periodic table. For the next element in atomic number sequence, the third dot is placed at the top of the symbol, the next to the right, and the next under the symbol. These 3 unpaired electrons occupy the 3 valence p orbitals according to Hund's rule. The remaining 3 electrons pair with the single electrons in the same order until the p sublevel is filled. In later chapters, we will discuss bonding between atoms. In bonding, the positions of the s and p electron dots can be shifted around the element symbol to best illustrate bonds formed with adjacent atoms. But the number of valence electrons does not change. Ionized atoms. Electrons move between energy levels within an atom when they gain or lose energy. Given enough energy, an electron can escape or be pulled from an atom entirely. Other atoms may acquire electrons to attain a more stable electron configuration. Losing or gaining an electron causes an imbalance in the number of protons and electrons, thus giving an atom a net electrical charge. An atom or group of atoms with a non-zero charge is an ion. Ions may have positive or negative charges. If an atom loses an electron, it will have a net positive charge because there will be one less negative charge compared with the positive nuclear charge due to the protons. Positive ions are called cations. If a neutral atom gains an electron, it will have a net negative charge when compared with the positive nuclear charges of the protons. Negative ions are called anions. Electron dot notation can also be used to represent isolated ions. For example, if a neutral fluorine atom gains an electron, it acquires an electrical charge of 1-. We indicate this by placing a superscripted negative sign, the one is assumed, to the right of the symbol to represent ionized fluorine. Similarly, a magnesium atom that loses 2 electrons will have a 2+ charge. Notice that instead of a +2 charge, we write 2+.